Okay, good evening, everyone. Good evening, ladies and gentlemen. Welcome this evening. My name is Greg Natterer, and I am the Dean here of the Faculty of Engineering and Applied Science. And I'd like to thank you all for coming out this evening and supporting our Speaking of Engineering lecture series. I'd like to extend a special greeting this evening to our special invited guest to my right here, Dr. Bilal Ayub, who is a professor of civil engineering and a director of the Center for Technology and Systems Management at the University of Maryland. I'd also like to acknowledge this evening Jeff Emberley, who is as you know, the CEO and registrar of Paganel. That is Professional Engineers and Geoscientists of Newfoundland and Labrador. He will come up a little later to speak on the topic of Paganel's sponsorship of this lecture series. Just a few housekeeping items. In the event of an emergency, we should exit this room calmly, and the main exit is just immediately to the right through the front entrance of the building. We would then go left and across the street where the muster station is in the business parking lot. So it's two exits. We exit at the back and then through the main exit, and the muster station in lot 22 to the left as you exit. Also, washrooms are to the left also as you exit this room. So this lecture series is one that we do throughout the year, and it raises the awareness of engineering among the general public, among students and the community, of the importance that engineering has in our everyday lives. We're very proud of the work that is going on within the Faculty of Engineering and Applied Science. And just to give you a recent example, two of our students in civil engineering, Molly Noseworthy and Janice McCarthy, placed second at a prestigious international competition that was held in Philadelphia last month by the American Concrete Association. This is the premier association in the world for concrete. And they won a mortar workability competition. So this is a competition that involved dozens of the top schools around the world that were testing the flowability and stability of mortar within a mold. They won second place, beating out many of the top schools. So just one of many examples of how we're proud of the wonderful accomplishments of our students. As I mentioned to earlier, this event is co-sponsored by Paganel. Paganel is an organization with a mandate to regulating the profession of engineering and geoscientists in the province of Newfoundland and Labrador. Protecting the public interest, it has over 4,000 members, and we're grateful for Paganel's support of this lecture series and honored to partner with them. So on to tonight's lecture. Tonight's lecture is about a very fascinating topic, and it's going to speak about how the risks are managed today for natural disasters. Natural disasters in 2011, as an example, resulted in hundreds of billions of dollars in damages around the world and over 30,000 fatalities. Storms and floods accounted for approximately 70% of over 300 natural disasters. Earthquakes producing the greatest number of fatalities in those numbers. Managing these risks nationally and internationally requires a new way of looking at resilience and metrics on risks associated with natural disasters. So, in this presentation, Dr. Ayub will discuss the resilience methods that meet a set of new requirements and relationships to better understand reliability and risk, particularly as it relates to natural disasters. These new metrics provide a basis for the development of effective decision-making tools in multi-hazard environments. Dr. Ayub is a distinguished researcher and teaches civil and environmental engineering, risk analysis, and economics, as well as applied mathematics at the University of Maryland at College Park. Many of you will know this is one of the top engineering schools in the U.S. His main research interests are risk, uncertainty, decisions, sustainability, and systems as it applies to civil, mechanical infrastructure, energy, defense, and maritime applications. So it's a pleasure for me on behalf of the faculty to introduce you this evening. Let's please all give him a warm welcome this evening.
Good afternoon. Acoustics are fine? Okay. Thank you, Dean Craig, for the fine introduction. Today I had a meeting with the Dean, and I was very impressed with the amount of energy and activities that are going in the School of Engineering. Also, I'd like to thank Professor Faisal for inviting me in here. I'm delighted to participate in Speaking of Engineering lecture series. The theme is on managing risks related to natural disasters. And I thought to cover a topic which is contemporary in nature. As you might know, there is big interest nowadays in resilience. We'd like to have our communities and society to be resilient to events that you could classify as disastrous in nature. So this is a field where the National Science Foundation, the Department of Homeland Security, the National Institute of Standards and Technology, among many other agencies, providing millions of dollars in funding to enhance community resilience. Okay. The outline of my presentation is shown in here. I'm going first to start by some background. I'd like to share with you the risk landscape globally. Then discuss the definition of resilience. What does it mean? Keep in mind that the term resilience has been with us for decades, and its use has extended many fields, and hence it will make its definition for our purposes a little bit challenging. Then we are going to talk about how should we measure it, measurement science related to resilience, followed by examples and practical ways of dealing with it. Because if we measure it, we can manage it. So measurement is key in this regard. Then I'm going to share with you recovery. Recovery is an element of resilience, and I'll focus on that because that piece is new for our risk practices. Then I'm going to discuss ongoing work and interests and finish with some concluding remarks. As background, as the Dean mentioned to you, in the year 2011, according to the United Nations Office for Disaster Risk Reduction, we had about 300 natural disasters worldwide, resulting in about $360 billion in direct damages. These are direct property damages, and about 30,000 fatalities. And I can tell you in general, the fatalities, the major share of the fatalities is really earthquakes, and the major share of damage, direct damages, tends to be because of flooding. For the U.S., the share of the U.S. in the year 2011 is about $55 billion. This year, 2011, it happened that we had the tsunami in Japan, which contributed significantly to the dollars in terms of direct damages. This figure shows the risk landscape globally based on the World Economic Forum. The World Economic Forum, which is held once a year, is primarily driven by economists. And you can see in here it's qualitative in nature. The horizontal axis is basically showing in here the unlikely, likely, and very likely on the x-axis. The vertical axis is showing an approximation of the potential damage. And I highlighted a few things in here that are of interest to us. One is climate change, which you see at the very top. So this is very likely, potentially large impact. And the vertical axis is in billions of dollars. And then there is storms and cyclones. which is also, it comes into the very likely and significant damage of about $250 billion. Now, this landscape, which covers, according to the legend in the figure, economic risk, environmental risk, societal risk, geopolitical, technological risk, and so on, that landscape, of course, changes from one year to another. And those economists, they convene every year to make changes to the assessment. If you are interested in such figures, you could just Google the World Economic Forum, and you'll see the most current report. And there are a series of figures of this type. Now, this chart in here is coming from basically a UN agency as well, and that's the economic and human impact of disasters in the last 10 years. There are 3 columns. My pointer is not working. Does this point? Okay. Anyhow, I could just, I thought if I could resolve it, I might need it in the future. I mean, there is the arrow in here. I could use this here. I think this will work.
The mouse. Yeah.
The mouse. Let me use the mouse. I think.
One keypad right here.
Yeah, sure. Perfect. Thank you so much. Sorry for, okay. And this chart is showing the economic and human impact of disasters in the last 10 years. And this column is damages. Here is the year that we were discussing, in the year 2011. And it happened to be the largest year in terms of numbers, but you could see in 2015, it was also a significant number. 2008, you could track those to particular events. And those are being tracked with some notes in here. People affected, these are not fatalities, but the impact on the lives of people, not in counts, in millions. You could see in here there's 260 million impacted, and that's basically driven by flooding. We're affected by floods. People killed, you could see a large number in here of 330,000. This is the 30,000 that I mentioned earlier. The number is slightly different depending on how you do the counting. But the year before, we had a larger count, and this is basically caused by basic 2 events. One, 70% of it came from earthquakes and tsunamis, and about 40% caused by other disasters. But in general, over a decade, we had $1.4 trillion in total damages. You could average that per year, which comes to about 140 million. $1.7 billion, 1.7 billion individuals were affected, and 0.7 million in terms of fatalities over a period of 10 years. Now, in this figure, we are, again, coming from the UN ISDR, is showing the count, how many natural disasters that happened over globally. Basically, they are shown by continent. This color is by continent, and this is per country, the largest within that continent, and showing only the top 10. And you could see Asia has the largest numbers in here, with a breakdown that's shown China as being the largest, India, Philippines, Indonesia. Then you have the United States. This is just sheer count. This chart shows basically 2 things. One is the economic damage, which is this bar chart. The reason of the 2 color coding to show the contribution of the most significant event. So if I look at, let's say, this bar, where we have losses of 250 billion, almost more than half of it came from one event. So what you are showing in here is the contribution of major events, and they are noted by name. So you could see in general, there is a lot of variability, but in general, there is an increase. But also the increase can be attributed to the increase in inventory of assets, that we have more built environment and so on, and people tend to favor areas that are prone to hazards for their, to establish their presence, meaning they would like to be in the coastal areas because it offers all type of benefits, and they tend to be most vulnerable or affected by hurricanes and so on. So there is correlation almost between the 2. The red line is showing the trend in terms of reported incidents. And you can see in here the counts, 413, 432, and so on. This chart, this is my last chart about the landscape. This is 2015 disasters in numbers. You have by event type, which is shown in the middle here, by hazard type, flood, storm, drought, and so on. And then we have two columns. One column shows the numbers for 2015 in terms of count, how many events happened. And this number shows the average over a period of decades. So it's showing how does 2015 compare to the average? Are we above the average, below the average, and so on? So you could see in 2015, we had 346 occurrences compared to an average, which is basically 367, and so on. And then it gives you the breakdown by hazard type, flooding, how does 2015 compare to the average over a decade, and so on. This is in terms of deaths, right? In terms of people affected, which is shown on this side, it's displayed in a similar manner. 2015, we had about basically about 100 million, while the average is 173 million. One of the hazards that I identified earlier based on the World Economic Forum chart is climate change. And one of the impacts of climate change is sea level rise. There are other impacts, but I thought to highlight sea level rise. St. John's will be impacted by sea level rise, approximately, I think, at a rate of 3 millimeters per year, which is similar to the rate of the Washington area. The Washington area, the sea level increase is about 3 millimeters per year. But you know, the concern is not only of the sea level going up, but the amount of volume of water that will be close to the town and so on. Because when you increase the sea level a little bit, the potential for surge will become bigger, and the magnitude of the surge will become quite substantial. The relationship is not linear. You increase 1 millimeter of sea level, it could translate to much more as an increase in surge height. I have two slides in here. One is showing Shanghai. The reason I'm looking at Shanghai because we have an ongoing study now with Tunji University to look at the impact of sea level rise on their newly built tunnel system for the metro. They have about 6,000 kilometers of tunnels for their metro system. Before I talk about the images, let me tell you about the Paris Agreement, the recent 2015 Paris Agreement. Basically, the agreement calls for not to exceed 2 degrees in terms of temperature increase, and ideally to keep it below 1.5 degrees. That's by basically 2100, and the reference point is pre-industrial level. So when we talk about 2 degrees, it's compared to pre-industrial level. At the present, we are at 1 degree. So really, we have 1 more degree to go to get to the 2 degrees, which is as specified by the Paris Agreement. And the idea is we need to keep it lower. Now, if you look at 2 degrees, which is this image in here, you could see that part of Shanghai will be flooded. I mean, this is more the financial center of China, pretty much. It's the equivalent of New York. And if it goes to 4 degrees, which is business as usual. In other words, without the Paris Agreement, the projections that it will go to 4 degrees, and you could see the extent of flooding as shown in here. The number of people impacted will be in the millions of individuals, as shown as stated in here. In the U.S., we have similar type of thing. I'm showing 2 images in here. One for New York. This is 2 degrees. Where this bowl is in the financial district where the stock market is, right? 2 degrees, it is fine. 4 degrees, you see just the tail. This is not counting surges, by the way. I mean, if you put in surge, when we had Hurricane Sandy, the surge magnitude was 13 feet. 13 feet in surge that hit Long Island, right? So increasing the sea level, my biggest concern is really the surge that will come with a storm. Now, if you look at Miami, which is a major problem in the United States, that's one of the most challenging problems in the States. At 2 degrees, that's the extent of flooding in Miami, and that is the extent of flooding at 4 degrees. You know, in Miami now, there is a new term that's coming up, which is nuisance flooding. This is flooding that happens almost regularly. So you'll have in the street, water will come on and so on. And people are managing to live with that. So that is becoming a major issue. Now, let me describe what's the impact of loss of assets. So I'm changing subject in here away from climate change, just I'm going back to resilience. The World Bank has a lot of interest in resilience and how to quantify it. And their focus is in the impact on the well-being of people, right? So they come up with a measure, which is, I stated in here in non-mathematical form. It's basically a ratio. It's called socioeconomic resilience. So for every dollar of asset loss, if I lose $1 in asset could be roadway, it could be anything, it will result into welfare loss, meaning it will affect people. If you quantify how it will affect people, then I could calculate a ratio. For every dollar, what's the dollar equivalent for affecting people? So the smaller this ratio is, the worse the situation. So this is the scale in here. It shows the resilience in this measure. Although we did some research at Maryland and we are proposing a different measure, because ideally, without getting into it, but if I look at this chart in here, 25%, it means that for every dollar of asset loss, you'll have $4 of welfare loss. And most of the impact, you could see the dark red. It happens in Africa, some in South America, and so on. The next range, you could see more in South America and Africa, and so on. Canada and the US, it tends to be in this range, 62 to 75%. Gray areas are areas where there aren't reported results. But that was based on values that calculated for 90 countries based on events, simulated events from 5-year return period to 1,000-year return period. So that was an elaborate study that was recently published by the World Bank. Now, this finishes the landscape and what's the impact of loss, asset loss, on well-being. Yeah. Let me move to the next item, which is resilience definition. As I mentioned earlier, resilience as a term is not new to us. I mean, for people who are in engineering, and assume most of you are coming from engineering, you use that term somehow in some field. In my case, my first exposure to it was in materials, that we'll talk about resilient materials. So there is use for it in materials science, but also it was used in other fields, as you can see in here. The formal treatment of resilience as a term, as well as a way to quantify it, is really in ecology. But again, people talk about neuroscience, economic resilience, community resilience, and all of the others that come in between. Systems resilience. The Holing definition, which comes from ecology, which is highly cited, is a 1973 definition. And resilience determines the persistence of relationships within a system and is measured as in the form of its ability to absorb a changed state. Thank you. Now, in our case, in recent work, we basically proposed a definition that lends itself for quantification. And this definition is the persistence of a system, which is more of an engineering system, but it could be any system. It could be a cyber network. It could be a transportation network, water distribution, any of the above. It's the persistence of its functions and performances under uncertainty in the first of disturbances. Now, in 2013, there was a presidential policy directive that came from the executive branch on critical infrastructure security and resilience, and it requires federal agencies, they have to quantify resilience and manage it. I know this figure is a little bit busy, but it's such a critical figure in understanding resilience, so I'm going to spend a little bit of time to explain what's in here. So what I have in here on the x-axis is time in years. On the vertical axis is performance. Performance, it depends on the system. This could be throughput of traffic. It could be throughput or distribution of water, the volume of water, or anything else. So the definition of performance, I'll give you examples in a minute, but the definition of performance depends on the system. Ideally, when we design a system, we place this at a certain target by design. We'd like to achieve a certain performance level. So this is the target, which is, I call it performance as new. But our systems, they age. So in general, they tend to follow a curve which looks like this. Although sometimes you could have improvement, which could be handled. But for now, let's say this is the aging aspect of the system. Now, we have disturbances. The disturbances, which could be earthquakes, flooding, any of the above, those disturbances happen at a rate which we are calling lambda, which is really a number of events per year. Right? This is a stochastic process. We don't know when it will happen, and not every occurrence will cause damage. I mean, sometimes you might have an event, but the system will continue to function without any effect. But in some cases, when that event happens, it leads into disruption. Now, that's the piece we are interested in here. So when the system fails, it could fail in any form. For people who are with engineering background, it could be brittle failure, which is what we have in F1, or it could be ductile failure or more graceful failure and so on. I could design a computer system that could be quite graceful network in its failure mode. The recovery starts after some period of time, and the recovery profile could follow any of those. We could recover it to as good as old, or as good as new, or worse than old, and so on. So there is a terminology that's defined in here. Now, what is resilience? Resilience in simple terms, without having the equations and so on, if you look at this total time, which includes the disruption period, this total time is an average total time, because I don't know when this event happens and so on. But I could compute the average of it. And then if I take that total time and examine the fraction of it when the system is functioning. So functioning divided by total time, I could define resilience. It's like % of being available. If I do that, and then I could bring in stochastic processes, all the random variables in, and the equation becomes bigger and so on. But in simple terms, it's the fraction of time when the system is operational and delivering the functionality that's intended. This partial functionality in here, robustness, which is when the system fails, sometimes it doesn't really fail to 0 level in performance. It might fail to some lower level. All of this can be accounted for within this equation. So that is the nature of the model that we are dealing with. Now, the vertical axis, which I mentioned that it has many meanings, I have examples in here by system type. I have houses and buildings. This could be the performance, the unit of measurement could be area, available space. Transportation could be throughput traffic, and so on. Water delivery system, coastal zones, communication, healthcare, communities, which is an item. In the US, there is big interest in community resilience. And if you'll ask, well, how can you measure the resilience of a community? What's performance for a community? There are several working with economists. And we've done a study for the Department of Commerce in this area. Working with economists, the way it's done is in terms of economic output. You could look at a community and see how long it will take for the community to bring its economic output to the level that it used to have before the event. Now, the shapes of curves that I showed you earlier, the nonlinear curves and so on, it might be very difficult to characterize in real life when you deal with certain systems. So we came up with a couple of approximations. One is what we call linear recovery, which is the curve in here. And we simplified the equation without getting into the details of it into a closed form expression. This is basically a practical model. There is no iterative solution, no numerical integration. It's just simple. And that's based on linear recovery. And also it does apply for 2 other recovery types. One is what we call single-step recovery and multi-step recovery. We examined many systems, and you'll find those 3 models, linear recovery, single-step, and multiple-step. They will cover a large number of systems. And the model that we have in here has several attributes that captures all the dimensions of resilience. One of them is how often the event happens, the failure rate, the event rate. What is the probability of failure of the system if the event happens? What's the residual, the initial, as well as the residual capacity or performance level after the event, what's the duration of the recovery, the duration of disruption, the recovery profile, and so on. The planning horizon enters into the equation as well. Now, life is much more complex than a single system, and we all know that we have multi-dimensions in here. And that's one complexity that we are dealing with, part of the American Society of Civil Engineers Infrastructure Resilience Division. If you look at this figure in here, there is a lot of 3 dimensions at least. One is we have to look at the hazards by different types. We don't have a single hazard. It could be earthquake, flooding, volcanoes, and so on, fire, and things of this type. Then we have different systems types, wastewater, and so on, transportation, communications, and so on. And then we have what we call the adverse event life cycle. This comes from planning, mitigation, response, recovery, rebuilding, and so on. Now, within each combination, if I want to consider each combination, I need to account for geographic location, where is it happening within the US? I need to examine the uncertainties and the risks, account for all the attributes of resilience in here, the project life cycle. So you bring all of this together, you could see there's a lot of complexity. So it's really system of systems. We have several projects that are going through the ASC Infrastructure Resilience Division at the present. We have about, I think, maybe 15 projects. Presently, I'm the chair of that division, where we are examining a good number of these items in separate studies that are mostly voluntary work, but it's supported with some small financial support through the ASC Infrastructure Resilience Division. In engineering, as designers, always we worry about safety. I mean, safety is a core principle for us, right? And then the way we dealt with it in terms of safety evolved over the times. We started, if you go historically, we started with, a safety through punishment. If a structure fails, then we need to, have penalty on the builder and so on, right? Then it becomes factor of safety, codified, right? Then we had a reliability-based design. Now we are accounting for uncertainties properly. Then it was followed by risk-informed design. And now there is big interest in what's called resilience engineering. How can I have the resilience built in as part of the design? And what's new in here is really recovery. I mean, if you look at what happened in Japan after the tsunami, recovery was reactionary. There was no recovery part of the design. I mean, they start to actually design robots and ice sheet wall to contain the radioactive material. So the question, I think the challenge for engineers, and that's the challenge for all of us, is how can we design our systems where recovery is considered during the design stage for certain failure modes. One of the disciplines where recovery is considered in the design stage is in naval architecture, is in subdivision, right? You could say, well, in submarines and ships and so on, we do consider flooding and how can we control it and recover from it through pumping and so on. In civil engineering, I don't think it's there, as well as in many other fields. I gave, in a public hearing for the Nuclear Regulatory Commission, I gave a talk about resilience, and there was big interest in terms of doing research pursuits in this area related to nuclear power plants. So let me take a few minutes just to focus on recovery, because it's something which is new when it comes to consideration of safety for our engineering systems. The Nobel laureate Becker in 2005, in an article, he basically gave very favorable review or examination of the work of John Stuart Mill when it comes to recovery. And basically, I'm quoting from the works of John Stuart Mill, that great rapidity with which countries recover from a state of devastation and the disappearance in a short time of all traces of mischief done by earthquakes, floods, hurricanes, and the ravages of war. That he was saying that, societies recover always in a manner that exceeds our expectations. And then Becker goes through to assess the claim by examining several cases, and he mentions some of those cases in his article. One of them is the September 11 attack on New York City, where, as you're familiar with the towers and so on, And the impact of that attack was minimal in terms of the GDP of the US. It did have local impact, but if you examine, in economic terms and so on, it did have little impact, which you could say, well, the economy is very resilient to it. Keep in mind that all of this is economic-centric, right? He's an economist who's talking about like this, right? The Kobe earthquake in 1995, 6,000 people dead, 100,000 homes destroyed, and again, the economic recovery was quite rapid. The flu pandemic of 1918 to 1919, 30 million people died, but the world was not connected the way we have it now. 2004 Indian Ocean earthquake and tsunami, again, large number of deaths and people displaced in 15 countries. The Asian stock market was hardly affected because of it. I took 3 cases to examine recovery. The first one is Hurricane Katrina. I'm not sure to what extent you are familiar with Hurricane Katrina, but this hit the city of New Orleans in the year 2005. Here is the map of the US, and we are over here, right? And that's the hurricane track going through Miami and then impacting New Orleans in this location. And this is a cross-section of the city from point A to point B. The city is surrounded by a river on one side, the Mississippi River, and we have on the top there is the lake. The lake is part of the Gulf of Mexico. So if you take a cross-section from A to B, that's what you'll see. So you could see in here the river, which is level, it will be higher than the lake, and there are flood walls or levees on both sides. So actually the city is in a basin, right? So if you have breach on any side, it will end up flooding the city. And when the breach happened on the lake side, it wasn't on the river side, that is the result in terms of inundation in the city. And that resulted into substantial area that was flooded. It's as big as the United Kingdom in terms of area that was devastated. Now, I wanted to examine recovery. This is a historic event. It happened in 2005, and I'm looking at the entire city recovery, right? I'm not looking at a particular system. So what I did in here, I went to economic reports, and I basically indexed or pinned everything to the year 2001, the US economy versus New Orleans economy. And you can see in here, in 2005, when the event happened, the New Orleans economy basically was impacted, and it took a decline. It doesn't really show as a dip, like what I have in the figure, because the resolution of this will not capture it in that regard. But it does show a slow decline, and the reason behind the decline, industries did not come back. You have loss of population. Until now, the population in New Orleans is at about 65% of what used to be in 2005. So basically, people left, but a good number of them did not come back. There has been changes, basically, in the industry base. But if I look at it in terms of economic output of the city, and then track it until you have a city which has more production than what's the average US, it will get me to somewhere in here. So you could say, well, the recovery, it could be as much as 6 years, 7 years. The shape of recovery is more or less is linear. And hence the need for that linear model in a simplified terms, because it could serve a very good purpose for our calculations. Another case study is the bridge failure that's on Highway 35 West. This highway goes to Minneapolis, and it's a major highway. It's an east-west highway. It's an 8-lane bridge, steel truss, arch bridge carrying Interstate 35 West, crossing the Mississippi River, and I think it was a fatigue issue that resulted into the collapse of the bridge, as you can see in here. Catastrophic failure. The bridge fell in the river pretty much. And I drove over that bridge a few times over the years, resulting into 13 deaths, 145 people in terms of injuries. It carries substantial, significant daily traffic of 140,000 vehicles per day. So the rerouting was quite significant. Immediately, the bridge was placed on fast-track replacement, and the event happened on August 1, 2007. On August 18, 2008, it was open as a new bridge for traffic. So it took 1 year. And that's the bridge before the failure, and that's after. And basically in here, you could say it is a single-step recovery, because you can't open it by one lane and so on. The last example I have is recovery profile for the World Trade Center of September 11, 2001. The event at the event and after. And basically, just to give you the timeline, this happened in 2001. Reconstruction started in 2006 because of litigation. They were all it was in the court pretty much between the Port Authority and the developer. And once they agreed on some terms, they started the construction and they opened the first tower 13 years later on November 3rd, 2014, from 2001 to 2014. And that's a single tower. And the impacted ones were several. So you could say, well, in here we have multi-step recovery. When you have a tower of this type, you don't really open part of it for use. Usually you have to get occupancy permit for the whole tower, and this could delay basically things until the tower is completed. Recovery has many complicating dimensions, and they are not studied until now, and that's an area where there could be opportunity for pursuing them. For example, interconnectedness and dependencies. People done a lot of work in dependencies related to failure. Like if I fail one system, there could be cascading failures and so on. You lose what happened in Japan. That tsunami destroys, pumping stations, cooling water does not go to the reactors, and then a major nuclear accident. So that dependency is important, and people studied failure-type dependencies. Recovery-type dependencies has not been examined. When you have a devastated city, recovery has to happen in some orderly fashion. And how things depend on each other in terms of recovery, it could have similarities with the failure recovery, but not necessarily identical to the failure-type recoveries. And these are some considerations that are related to recovery. The last item I have is the economics of resilience. At the very end, once I quantify resilience, I'd like to enhance it. And to enhance it will require resources. And to expend those resources, they have to demonstrate value. Meaning I'd like to examine, basically, if I spend $1 in enhancing resilience, how much return I'll get in economic terms, in terms of reduction in the losses, the potential losses. So there is a whole notion of economics of resilience. This is a project that we've done for the National Institute of Standards and Technology in this area. And basically, the foundation for it is in economic valuation. What is the value of an item? Right? The value of an item, which goes into economics, the value of an item has to have some basis. There has to be a way to measure that value. In general, what's accepted that the value of an item is anthropocentric in nature, meaning the value of an item is measured in terms of how valuable it is for human beings. Right? I mean, this is the accepted practice. It should cover what we call all instrumental values. It should allow for substitution, economic substitution. It should factor in individual preferences, including the desire to live. And this should be aggregated through the society, basically by its governance system. So if you bring all of those together, you could see that the valuation has really a lot of complexity in here, economic valuation. Now, economists came up with different methods. They're all, I could say, they are anchored to labor theory of value. But the most accepted one is what we call willingness to pay. So if I have, let's say, a pen, and I'll ask you, what's the value of this pen? The value of this pen is not how much material went into it and how much it cost me to manufacture it, but it's how much somebody else is willing to pay for it. It's market forces. So that's called the willingness to pay. So the value of an item is measured by the willingness to pay by somebody else for that item. Right? And that could be, by the way, a problematic definition, but that's the accepted definition. There are many issues with that definition, but I think that's the best that we will have. So in doing the economics of resilience, what we do is basically several things. One is we'll do what we call loss accumulation. I'll establish a planning horizon, and I'd like to know in stochastic terms, in probabilistic terms, what is the total loss, the aggregate potential loss over that planning horizon. Then I'd like to know the cost of taking an action, and how would it affect my cash flow when it comes to losses, the potential losses. So it's almost I'm comparing two cash flows. One is before I take an action. The cash flows, they are losses due to events, right? And after I take an action, I'll have a different cash flow. I need to compare the two cash flows to see what's the net difference in probabilistic terms and compare it to the cost, which is my investment. This will require introducing a discount rate, and discount rate is an item which is, has to be handled carefully. And in general, I could tell you simple rules. The longer the planning horizon, the smaller the discount rate. Because if you are looking at planning horizons of 100 years and 200 years, the discount rate could be really small, maybe 1% or even 0. Otherwise, you'll end up discounting things that are of the future and basically taking things from future generations. So it has to be a balancing act of how to figure out that discount factor. Now, the model that we use in here is similar to what's used in the insurance industry. And this is a citation of a recent publication with an economist from the Department of Commerce related to this subject. At the very end, what we do in economics, this is our original, the figure that I discussed earlier. All I did in here, I added to it 3 histograms, 3 distributions showing dollars, basically impacts. Why do I have 3 curves in here? They are color-coded to correspond to this part of the curve. So when the event happens, I have a loss distribution. Right? When we build, I have a recovery cost. Then during the disruption period, where I don't have the system available to me anymore, or it's partially available, I have indirect loss, which is basically loss of use. So the economics of it comes into 3 pieces: loss of the asset, rebuilding it, and loss of use. Imagine if you have a car, you total the car, you lost the property. If it wasn't insured, you have to go and buy another car. And in the meantime, until you figure out which car and so on, you lease a car. So these are the 3 pieces. Now, which one you should include and which one you should exclude, it depends on the perspective of the decision maker. An economist, a federal government economist, might not include all of this. They might include only direct losses. And the reason behind it, because they will consider what someone spends to lease a car is a gain to somebody else who leased you the car. So it's a net sum, a zero sum basically, in terms of the economy. It's really a transfer from one entity to another. The same thing with the recovery cost. The recovery cost, yes, you are building a new house or some, but then there is a builder who's earning the money. So that's considered to be a wash. So most of the time, the bookkeeping or the accounting for things depends on the perspective. Now, once those costs are characterized, and there is a lot of uncertainty in them, and I worked with economists over the years. Engineers, we tend to calculate things with high precision level and worry about all, the number of significant digits. And then you'll bring the result from the economist, which is the second piece of risk analysis, and you'll be rounding things to the millions of dollars and just all approximate and so on. And then you are trying to bring the two where the level of precision and accuracy and so on drastically different. But at the very end, we have to account for those uncertainties, and typically we do it in the form of a probabilistic framework where we calculate what's the probability that the benefit divided by the cost will be larger than 1. And when the benefit is larger than the cost, this is good, right? But because of the uncertainties in the benefit and the cost, there is a chance that the benefit will not be realized. That if the benefit becomes smaller because of randomness and uncertainty, and the cost becomes larger because we'll end up spending more, then there is a chance that we'll end up not realizing the benefits that we are claiming at the beginning. I think this is my last slide, but basically what I try to do in here is just give you the landscape, the risk landscape at a global level, related to several sites, and then focus on resiliency or resilience, which is an area of new interest when it comes to safety, and share with you what's going on now in the field, and where are the opportunities. I think the opportunities are, I could say, in the recovery end, interdependencies, and bringing system of systems, metrics related to various domains. All of these are opportunities for pursuit. And then the economics of resilience, which will enable decision-making in a rational and consistent manner. That's what I have, Dean. Thank you.
Thank you very much, Dr. Ayub. It's certainly a very informative presentation. I really enjoyed it. And so at this point, I'd like to open it up to the audience if there are any questions. And I will come by with the microphone. Why don't I start it off? So I was curious. You showed Miami, Florida there in one of the slides, and you were talking about climate change and natural disasters and the hurricanes. And so it reminded me when I was at a conference just a couple of years ago in downtown Miami, and it was at a hotel, and you could see that it's pretty much right on sea level, like in the downtown core.
Yes, right.
And I was fascinated by the fact that there were about 6 or 7 major new skyscrapers that were huge buildings being built right in downtown Miami, right along the coast and at ocean level. So I was wondering, where is the economics of resilience there in terms of developers, where we know ocean levels are rising, we know the issues with the hurricanes and natural disasters. So how is it that, what will it take for, I guess, economic development in places like that to factor in the risks involved and the resilience? And basically, I'm just curious how developers are doing this in a time when they know in very short order that there are going to be major challenges with them doing it. So that's just a question and a comment.
Well, thank you. This is a timely question. In fact, I was reading an article in Wall Street Journal, and the report was focusing on the lag between market value of property and the fact that sea level is rising. And they were discussing the subject along your questions. And basically, the reporter was making a note that until now, the market value of property has not been declining. It's in a stagnant stage. They are not rising as much as other parts of the country. And he was providing examples in Florida as well as Texas and Mississippi and so on. For developers, at the very end, if they can sell the property, I'm not sure if they will care too much, right? I mean, they are in a business transaction. So you'll wonder, maybe does the government should have a bigger role in this? But if it is left to economic forces, then it will be really tied. It will be tied to the market value of properties. As long as they can sell, they will continue to build. And until now, it's showing some signs of strain in terms of stagnation, but not in terms of decline. Yeah. Thank you.
A question, Dr. Ayub, about your last slide. Sure. And you showed there mostly what I thought were the costs. And I guess part of what your second last slide, what types of things and costs would a person or an organization do to create a more resilient system? And how would it be reflected in your graph?
I see. Well, the way it will be reflected in the graph, it will end up basically creating a resilient system. It could be achieved in several ways. One is to make the robustness higher, meaning when the system fails, it doesn't go all the way, further in the chart, right? Robustness. How can we achieve robustness? It has to be, system specific. I mean, we have to get into the details of what type of system. Is it a building, a bridge? What's the details of it, right? When it comes to civil systems. The other way we could enhance resilience is perhaps by introducing more of the ductility, right? Which we've done in earthquakes. I mean, we do introduce ductility and so on, And the third one is through recovery. And we have some work going in the recovery area to enhance recovery at the University of Maryland related to earthquakes. When an earthquake hits a city, a big task which has to be undertaken almost immediately is to know to assess the damage in all the buildings. And what they do is they will go around in all the buildings and basically put marks on them. If it is a red mark, an X, meaning nobody should enter, and so on, right? And this could be quite substantial effort as well as uncertain effort, because imagine if you enter a building and all the drywall is not cracked and so on, you are inclined to say it is fine, right? While it could be that the damage is in the structural member behind the drywall. So what we try to do is come up with structural configurations where there are fuses. So if there is a failure, I don't want the failure to happen anywhere. I want it to happen in a predetermined location. And I'll have that to be accessible for inspection. So it acts like literally a structural fuse. Right? In water distributions, pipelines, the city of Los Angeles, working with Japanese companies, they are doing something similar, that they would like to have the pipeline failure to be at a fuse location. So I could see this will affect the recovery, right? Because the recovery becomes less uncertainty and expedient.
So the cost would be an additional cost, and it would result in changes to these curves. Is that it?
Absolutely. So basically, reduction in recovery will reduce the blue curve, right?
Yes.
The magnitude, and direct impact also, because maybe will be impacted. Loss of use. All of these curves will end up adjusting. Yeah.
Thank you.
Yeah. Thank you.
Usually I pose a question, better or worse. A young lady who graduated a few years ago in sociology, I believe, looked at the reaction looked at the question of resilience in the communities affected by a major flood here associated with a hurricane, Igor. The resilience had much more to do with social factors, the cohesion of the communities, and the resources, often fairly simple resources, boats, sometimes small dynamos for lighting, etc. How do you factor into your scheme of things the social processes, which certainly were very dramatic here?
That is a great question. In fact, that's what exactly the World Bank report in 2016, that's the item they try to deal with. So the gap from asset loss to welfare loss, why in certain countries we have, for every dollar of loss, we have more dollars of welfare loss. Most of the time it's tied to social programs that basically, and there are many of them. You could have insurances, social programs through the private sector, or it could be through the government. How the cohesion of the society, how organized the society in general, and whether it's churches, religious institutions, and so on. Law and order could play a major role, and that the notion of welfare loss compared to asset loss will try to capture that social dimension. Now, in the rest of the presentation, I didn't really deal with that subject, right? And it's by design, because I wanted to focus on the infrastructure aspect of the resilience. Right? But to complete the study for a community, it does require looking at the society in terms of social programs and the cohesion of the society and all of these considerations. If that's an area of interest, I strongly recommend just searching for the name of this economist, 2016, the World Bank. It's a very interesting, quite detailed study on this subject. I do not totally agree with the models that he's doing there, but I think it's a leap forward in terms of the thinking.
I have one question, which is like, can you please explain what is the difference between single-step recovery and multi-step recovery? And second important thing, how we will quantify that, because till now we couldn't be able to quantify the recovery in terms of resilience. So how you will differentiate or quantify the recovery in terms of single-step recovery and multi-step recovery?
Okay. I mean, the example that I used for single-step recovery is the bridge example. You lost the bridge. We can't open a partial bridge. We couldn't open it by lane. Then when the whole bridge is back in operation, then the system is back to full capacity the way it used to be. Or it could be even the capacity is more than what we started with. I mean, when the bridge collapses, it doesn't mean we have to replace it in kind. We might replace it in an enhanced form. But that will be a single-step recovery. In the case, a second example that I used is if you have a district with multi-towers and it was impacted. I mean, this could be earthquake, or it could be, in our case, the event, the 9/11 event. So it destroyed multiple towers, and the way things are being built and opened for use is one tower at a time. So you could say that to bring it back to the way it used to be, in maybe millions of square foot in space, it could come in steps. Each step will correspond to the opening of a tower. But how can we quantify those for various projects? It does require deep thinking about the project. I mean, it's really case-specific, domain-specific. But I did find, based on what we examined so far, that the three models of linear recovery and step recovery will capture a good number of the cases that we have to handle. And keeping in mind as well that single-step recovery is a special case of the multiple-step recovery. So really, we have two, either linear or multiple step. I mean, you know, I attended I was invited to review on a panel review for the national academies on related to resilience, but the focus, it was for the Army Corps by the academies, and the focus was on natural environment, meaning, you know, coastal areas, dunes and barrier islands. If there is a damage, how can we quantify resilience and so on? And it was conceptual what the Army Corps did so far, and they were showing those fancy resilience recovery curves. I mean, it almost looks like a second order or third order function. And always I wondered, how can you come up with that function? Right? So, I mean, that level of precision is not justifiable. We'll not be able to characterize it that way. We'll be lucky if we can figure it out as linear or multi-step and so on. So we just completed a study for the Corps, for that group, related to metrics of resilience for natural environments. Yeah, here.
You talked about the measurement of resilience, and it's kind of taking the global system output and monitoring it, and that more or less tells us how a system is resilient. But if we want to start incorporating resilience into designs, we have to know why the system is resilient, and that requires, I think, a little bit more subtle, more localized changes within the system and seeing how that affects the overall output. I have my own views on how it might be carried out, but I wanted to hear yours.
Well, you know, the whole area of resilient engineering, I could say, is upcoming and emerging field, right? So I'm not sure if it is fully developed and mature, which will make great opportunities for research pursuit, right? I don't think there will be solutions that are general across domains, right? I mean, the only thing comes to mind is similar to what I was talking earlier, is those fuses, right? If I could define in general, this is now looking at systems in general, it could be anything, and basically come up with a fuse that will deal with that event, that disturbance, that failure mode, depending on the domain. And the fuse might vary in nature from one system to another. I mean, I was on a panel that on a working group that was created for the governor of the state of Maryland, the former governor, and it dealt with power loss. And the concern was in the long duration it takes to recover power. This is electric power through the distribution line, not transmission, but distribution. And we had two power companies, the major ones in the Washington metropolitan area, PEPCO and BG&E. The PEPCO gentlemen, and those, keep in mind that you need to keep in mind that the utilities, they don't like to share information, right? So they are regulated, but they have to be, they are very careful in sharing information. So the gentleman who's from the one utility company, he said that they are working on it. The biggest issue in the Washington area is the canopy of trees. We have it's one of the largest canopy of trees maybe in the whole US. And the minute there is, some branches falling down, they'll end up cutting the power and so on. So he said we did a lot of work in enhancing the strength of the cable. And we got it to a point where the cables are very strong. You fall a branch on it, it doesn't really, you can't cut it. But what started to happen is the poles will snap. Yeah. So now, to replace a pole is a major task than replacing a wire, right? I mean, that one will require much more logistics and so on. So you could see now how the failure has to be by design, where it fails and how and so on. And I think if we do that across the board, whether we are dealing with a cyber network or transportation network and so on, as much as possible, buildings and so on, we might be able to enhance resilience. And this could be part of engineering for resilience. But unfortunately, I don't have the answers fully for your question. It's a big question here.
Me either.
That's right.
Okay, I don't see any further questions. So at this point, I'd like to just say again, we really appreciate you coming to see us here in St. John's, giving this presentation, Dr. Ayub. It was a very fascinating presentation, and we've learned a lot. And I'd like to just say now, on behalf of the Faculty of Engineering and Applied Science, I'd like to thank you in person with the small gift of our appreciation. So let's give them a round of applause once again for coming.
Thank you.
It's a wonderful talk.
Oh, thank you so much. Thank you.
So at this point, I'd like to invite Jeff Emberley to the front to say a few words on behalf of Paganel.
Thank you, Greg. And as Greg said, I represent professional engineers and geoscientists, Newfoundland and Labrador, basically a regulatory organization, a licensing body for engineers and geoscientists. And I think most people in the room are aware of what Paganel is and what it does. And it's important for us to be here as part of this function, we feel. Trying to get the word out on engineering matters is an important part of what we do, and we feel that this is a very significant part of it. In terms of moving on to working with MUN, we work quite closely with Memorial University on a number of matters, and this is a good example of it. We work on, for example, the accreditation of Memorial students comes through our national body, Engineers Canada, working with accreditation across the country, and that's an important part of the licensing of engineers. And we also work closely with Memorial to ensure that they're informed as to what is required for licensure. And also we work with Memorial on a much more informal basis on a number of things. Reflecting on Dr. Ayub's presentation, I really appreciated this presentation. Climate change and many other factors are increasingly stressing both our natural systems and our man-made systems, and they really impact on us all. Dr. Ayub noted that managing these risks before the events occur and thinking about them can bring a lot to us. I was impressed, for example, about the breadth of his presentation, the implications for it across all fields. Not often do you get a presentation that affects everyone's discipline. The nature of us as engineers is we're all specialists in our own areas. And to have a presentation that really impacts everybody's discipline is really refreshing to see. You mentioned the electric utility business. Well, I'm an electric utility engineer. That is my background, and many of the things you say struck home to me as I was a planning engineer, and